Welcome to this explainer. Today, we're taking a deep dive into the fascinating, chronological evolution of the unsung hero of your car's engine, the connecting rod. You know, it's a part of our daily lives that almost no one ever actually sees, but without it, the modern world would literally grind to a halt. So we're going to explore how the manufacturing of this single component has evolved from an era of sheer brute force to one of microscopic chemistry and, honestly, some highly ingenious intentional destruction. Let's get right into it.
Think about it for a second. To really understand the massive engineering challenge here, we have to ask, how does a hidden metal component withstand the violent, explosive forces inside an engine, mile after grueling mile? Inside an internal combustion engine, thousands of controlled explosions are going off every single minute. The connecting rod sits right smack in the heart of that chaos, translating the violent energy of those blasts into smooth forward motion.
At its core, the connecting rod is the ultimate middleman. It's what turns the up and down pumping of the pistons into the spinning force that eventually rotates your tires. Now, that sounds super simple on paper, right? Just a solid link between point A and point B. But when you look at the actual physics of what is happening inside that combustion chamber, the job description of this specific piece of steel is, well, actually scratch that. It's borderline impossible.
The nightmare environment the connecting rod lives in is extreme. It is constantly subjected to cyclic, dynamical, tensile, compressive, bending, and shear loads. Okay, to put that into perspective, imagine trying to pedal a bicycle, but an elephant is repeatedly jumping on the pedals while you do it. That is the level of relentless cyclic stress these rods have to endure thousands of times per minute. To make a part survive that, engineers have had to get incredibly creative.
Section 1. Brute force, traditional casting, and forging. Let's start our journey in the past with the traditional methods used to shape these crucial components. For decades, it was all about heat, pressure, and just hitting metal as hard as mechanically possible.
Back in the day, engineers relied heavily on casting, pouring molten metal into a mold. But while casting works fine for lighter duties, the absolute extreme forces of automotive combustion demand something way stronger. Enter hot forging. Forging became the industry standard for high-stress applications because it doesn't just shape the metal, it physically compresses the molecules and aligns the internal grain structure perfectly along the load paths. This gives the rod maximum strength and fatigue resistance.
So how does this brutal process actually work? First, you cut a steel blank. Then you heat it way above its recrystallization temperature. We're talking up to 1,250 degrees Celsius, which is over 2,200 degrees Fahrenheit. At that crazy temperature, the metal is malleable enough to bend to our will without losing its structural integrity. From there, it's shaped through roll and closed die forging, trimmed of all the excess material, heat-treated, and finally shot-blasted totally clean.
But here is the truly mind-boggling part of this traditional method, the sheer pressure involved. To achieve that near-net shape blank, a massive forging press drops down with an extreme pressure of up to 2,500 tons. Let that sink in. That is the equivalent weight of about 400 full-grown elephants crashing down onto a single piece of glowing hot steel, all just to ensure it won't break inside your engine. But let's be real, you can only hit things with bigger hammers for so long. As engines demanded more precision and higher efficiency, engineers shifted from brute force to chemistry. Section 2. Enter chemistry, the powder metallurgy era. So, in the powder metallurgy process, instead of starting with a solid billet of steel, we literally start with microscopic dust. A super high-tech base powder is blended with specific alloy elements under exacting standards. This metal mix is then compacted in dies under tremendous pressure at over 1,500 degrees Fahrenheit. Finally, it's hit with a 750-ton hot forging press to create an incredibly dense, solid component.
Now, you might be wondering, why go through all this trouble with powder? What makes this really fascinating is that powder metallurgy totally removes the directional weaknesses found in the grain structures of traditional forging. By controlling the exact chemical makeup at a granular level, engineers create a material that is highly controlled and strong, yet uniquely brittle in a very specific way. And it turns out that exact property is perfectly primed for our next massive manufacturing breakthrough.
Which leads us perfectly into Section 3, Intentional Destruction, Fracture Splitting Technology. This is, hands down, one of the most clever innovations in modern manufacturing history.
Okay, so to install a connecting rod onto a crankshaft, the large end of the rod has to be in two pieces, the main body and the cap. The old way of manufacturing this required forging them as one solid piece, then painstakingly sawing them apart, cutting them, and heavily machining the interface just so they could be bolted back together.
It was super expensive and often resulted in slightly imperfect mating surfaces. The new process? Engineers literally just cracked the solid ring of metal right in half. Because the break is perfectly jagged, cracking the rod creates a unique, 3D puzzle piece fit that can only mate with its exact other half. There's no other way it goes back together.
Here is how this ingenious trick works in practice. First, a tiny, precise, prefabricated crack groove, which is called a kerf, is cut into the inside of the big end of the rod using a laser. Next, a wedge-shaped thrust pin is shoved into the hole. Finally, an instant massive impact load is applied right to that wedge. Snap! The metal breaks instantly along the laser groove. When you bolt those two jagged halves back together around the crankshaft, they interlock so perfectly that it completely eliminates any relative motion or shifting under stress. It is absolutely brilliant.
The sheer scale of the efficiency gained here is just staggering. This single moment of intentional destruction solves multiple problems all at once. By replacing sawing and machining with a single, violent crack, manufacturers see a 25% reduction in tooling costs, a massive 40% reduction in energy consumption, and a 30% cut in processing time. And the end result? A connecting rod that is 13% lighter and, amazingly, 30% stronger when subjected to fatigue loading.
But the evolution absolutely doesn't stop with fracture splitting. The relentless modern quest for efficiency brings us to Section 4, the lightweight future, sheet metal and hydroforming.
So why are we so obsessed with making this specific part lighter? Well, trimming fat off the connecting rod drastically reduces the massive inertial forces violently thrashing around inside the engine block. Lighter rods carry less momentum, which drastically reduces a phenomenon known as piston slap. That's essentially the piston awkwardly knocking against the cylinder wall, meaning the engine runs so much quieter. More importantly, though, pushing less dead weight up and down thousands of times a minute directly improves your vehicle's overall fuel consumption and significantly lowers emissions. It's a massive win-win.
Instead of a solid, heavy chunk of forged steel, engineers are now looking at entirely new form factors. In modern hollow rod designs, the future relies on taking sheet metal, stamping or embossing it into two distinct halves, and then permanently joining them using incredibly advanced methods like precise laser welding or diffusion bonding. So you end up getting the exact same outer dimensions, but with a completely hollow core.
Or, get this, an alternative cutting-edge method achieving a similar hollow result is hydroforming. Honestly, this feels almost like science fiction. Instead of a press stamping from the outside, incredibly high-pressure working fluids are pumped inside a raw steel tube that sits inside a die. The liquid pressure actually blows the steel outward, almost like a metallic balloon, expanding it perfectly into the shape of a connecting rod. It requires significantly less energy than traditional hot forging and creates a remarkably robust, single-piece hollow part.
And the numbers backing up these new hollow designs are stunning. By transitioning to these sheet metal and hydroform designs, engineers anticipate an incredible 25% reduction in component weight. Just think about that. Taking a quarter of the mass out of one of the hardest working parts of an engine, all without sacrificing the tensile strength required to survive combustion, that is a monumental leap in mechanical engineering.
And that brings us to the core philosophy driving all of this innovation. As our sources point out, lightweighting of the connecting rod will therefore help decrease the inertial component of the loads and lead to improvements in fuel consumption. This constant drive proves that even the most hidden, unglamorous, dirty parts of our machines are constantly evolving in laboratories and simulation software to make our technology greener, quieter, and hyper-efficient.
So, as we wrap up this explainer, it leaves us with a provocative thought. As we demand more eco-friendly and efficient vehicles, transitioning to advanced hybrid setups, or alternative fuels like hydrogen, what other unsung mechanical heroes hiding inside our machines are just waiting to be reinvented? The connecting rod went from a brute force iron club to a laser-cracked, hollow marvel of fluid dynamics. It really makes you wonder what the next decade of manufacturing miracles is going to bring. Thanks for hanging out with me on this deep dive, and keep your curiosity revved up.